Okay, good morning, all of you. So this is a course on large language model. This is a new course, and in this course we will talk about recent advances in large language models. This is an advanced PG course. So the hope is that so we'll keep the introductory part of LLM short, and we'll focus more on the advances of LLMs. Okay, and this is an ELL 881 course. It is also cross-listed with a School of AI course, AIL 821. So my name is Tanmay Chakraborty. I am the lead, instructor for this course. I am an associate prof in the electrical engineering department. I'm also associated with the School of AI. I work in NLP, and along with me there are 5 other instructors who will also teach some parts of this course, right? Professor Sauri is from DICT, and 3 researchers from IBM, Yatin, Dinesh and Gaurav, and also Manish Gupta from Microsoft. And the course TA is Onnoy, sitting here. He's my PhD student. So this is the course directive. So we have slot H, and this is the website that we will follow. Okay, so all the lecture materials, recent papers, video links, everything will be uploaded to the website. So please follow this website. And this is the tentative marks distribution. We have major and minor 15 marks, major 25 marks. There will be 2 quizzes, one before minor, another after minor, 10 marks. Assignment, there is only one assignment. Okay, so and we also have a mini project. Mini project has a major component which is 30%, and it's a group based mini project. So we'll talk about the mini project later. Audit requirement is B minus. Okay, so course project, the idea is that you will have to choose a project. The project, I can float a set of projects, right? Maybe in 10-15 days, but you are also welcome to suggest your own project ideas. Okay, so each group consists of minimum 1, max 2 students. And what is the expectation? The expectation is that you develop a new model, you evaluate your model, you benchmark it, compare it with baselines, you prepare a presentation, you write a report, and you submit the data repo and source codes, right? Create your own GitHub, own Git link, and then there's a presentation at the end of the course, which actually consists of 10% of the project. Okay, so this is very important for any assignment, quiz, writing the report. Please do not use any generative AI tool, right? Please do not plagiarize. If you want to, you are welcome to collaborate. You are welcome to discuss with me, with your friends, right? But please do not copy anything from any sources. If you think that some things need to be copied, you rephrase it and cite appropriately. Okay, and we will strictly follow this guideline, the institute's plagiarism guideline. Okay, as I mentioned, this is an advanced graduate level course, right? And we will essentially will essentially read a lot of papers, recent papers, right? And I hope that, this is not a traditional kind of graduate level, undergrad level course where we have exams and other assignments. There are also assignments, but this is more of thinking, right? And the expectation is that you think about it, you reason about it, and then you also you are welcome to interact with me and the other instructors. Okay, so this is the course content. I will elaborate on each of these separately. So we'll start with basics. Okay, we'll have one lecture on the introduction of NLP. Okay, so as you can understand that this is an advanced NLP course per se. So the hope is that you know basics of NLP. So in alternative semester, I teach this ELL 884 course, and I think that there is another course in the CS department, right? So if you have taken those courses, you are good to go. If you have not taken these courses, you can possibly go through any online sources, okay, and you get basic NLP knowledge. There is one lecture on what is a language model, right? We'll introduce statistical language model and different types of issues with the statistical language model, and then we will discuss different types of word embedding methods, word to vec, glove, first text, and so on. Then we will move to neural LM, right? Specifically CNN, RNN, sequence to sequence methods and attention. So this part is a basic part of this course. It won't take more than couple of weeks maybe, right? And then we'll move into the architecture of the LLM, actual architecture of fundamentals of LLM. We'll introduce transformer, and then different types of learnings of transformer, encoder only, decoder only, encoder decoder model, advanced attention model. We'll talk about multi-query attention, grouped query attention, sliding window attention, flash attention, rotary positional embedding, and so on and so forth. We'll also discuss mixture of experts. It's a new paradigm, right? Some of you know, basically the idea is that you have heterogeneous modules, and heterogeneous modules have expertise in different domains, and then these modules essentially are interacting through different gating mechanisms. So we'll talk about mixture of experts. The third component is learnability, and here we will discuss topics like scaling laws. We will see how language models, how LLMs essentially can be better off with more and more parameters, more and more data. We'll also talk about contradictory results, which essentially show that maybe scaling law is not a good idea. Then we'll talk about emerging properties, prompting, instruction fine-tuning. We'll talk about different types of alignments, right? DPO, PPO, KTO, and so on. And then we'll discuss distillation methods, right? Basically designing lightweight models and parameter efficient models. We'll discuss knowledge distillation methods and parameter efficient fine-tuning, right? LoRa, ADA-LoRa, these kind of methods. And then we'll also talk about efficient and constant LM inference, okay? So the last part is mostly on user acceptability, and here we will discuss advanced RAG methods, retrieval augmented generation methods. We'll also discuss multilingual methods, vision language methods, models, also talk about reasoning, because reasoning is one of the important aspects. And then we'll focus on handling long context, right? Specifically in the context of codes, right? And we know that code, handling code is very important, and when it comes to handling long context, code is important, because code, we see a long range dependency, and most of the models, most of the LLMs don't work in handling codes. And then we also talk about model editing. So the idea is that, let's say if you know that a model is already erroneous, or some factually incorrect statements are already embedded into the model, how without less supervision we can update the model, right? So that the model produces correct answer. And the last component is basically different ethical issues in LLMs, right? We'll talk about bias, toxicity, hallucination, and interpretability, mechanistic, non-mechanistic interpretability. And the last component will be essentially a recently introduced idea of state space model, where we will see models like Mamba, right, where the traditional state space models like RNN, HMM types models can be integrated to transformer kind of architecture for better processing, right? So this is the course content. So and as you see, this is mostly advanced LLMs, I would say, right? Okay, so this is the prerequisite. So I always say that there is no such predefined prerequisite for any course, but if you have excitement about the language, and if you also have willingness to learn something new, you can take this course. But officially, the mandatory prerequisites include data structure, algorithm, Python programming, of course, machine learning, deep learning. Desirable, as I mentioned, you should know NLP well, otherwise some of the concepts may not be very clear. So which which parts this course will not cover? This course will not cover anything about generative models which are not text based, right? We will not cover, let's say, image based generative model or vision based generative model. We will not talk about stable diffusion, for example. We will not talk about DALI, Mid Journey, for example, right? This course will not teach you coding. So the assumption is that you are aware of Python coding. Specifically, you are well accustomed with Hugging Face, right? Different libraries. Then you know how to handle a collab and so on and so forth. So if you want to know more about NLP, this is the site which I regularly maintain. This is the ELL 884 slide website that I taught last semester. So you can go through some of the materials over there. Reading materials, book wise, there is no book as such, right? But hopefully at the end of this course you will see a book. But if you want to know more about NLP, maybe of course the Bible for NLP is this Jodorowsky Martin book, Speech and Language Processing. There are also other books for NLP, advanced NLP, and also deep learning. But what we will do, we will mostly follow papers published in these conferences, ACL, EMNLP, NACL, NeurIPS, ICML, ICLR, KDD types conferences, and we also follow papers published in journals like TACL, TMLR, JMLR, PAMI, and so on. And this is the paper repo that you should regularly follow. This is ACL Anthology, right, where all CL conferences, computational linguistic conference papers, are archived. So you should definitely check out this repo. And of course, so you see, all of you know that every week thousands of papers are archived on which are related to LLMs, ML, NLP in general. So this is the archive subject that you should follow regularly, computation and language, right? And if you have some sort of notification on this, you will get papers which are submitted to this particular theme of archive. Okay, so this is the link that you should follow. Okay, so the last part of this prerequisite, so and the course directives. So many slides that I am going to use for this course are taken from some of the very famous, well structured online lectures, right? From CMU, from Stanford, from other parts, right? Mohit Iyer's course, UMBC course, and Michigan's course, and so on. This is of course a non-exhaustive list of courses from where I have taken slides. So I duly acknowledge all the instructors' effort to prepare the course material. Okay. Okay, so we have a separate lecture on language model, but just to introduce the concept of language model, since this is about LLM, large language model, we first need to understand what a language model is, right? So a language model is essentially a probability distribution over a sequence of tokens, right? So if you are given a token, a sequence of tokens, a sequence of tokens can be a sequence of characters, or a sequence of words, or a sequence of images, sequence of numbers, right? And these images, characters, words, subwords, these are tokens, right? If you are given a sequence, the language model should be able to say that the probability of the sequence is, let's say, 0.9 or 0.8, right? And how good the language model is solely depends on the kind of probability that it returns, right? Let's say if the if the sentence or a sequence of tokens, remember I will use the term sentence very vaguely, right? Because a sentence may not be a valid sentence, right? But I will use the term sentence and a sequence of tokens interchangeably. So let's say if the sequence is the monsoon rains have arrived, right? The language model should be able to say that the probability is 0.2 or 0.3, 0.4. If the sequence is monsoon the have rains arrived, the probability will be 0.001, right? So the model should be able to say that this is not a valid sequence syntactically, right? It may also happen that let's say there is a sentence like the mouse eats the cheese, right? The probability is 0.9. The cheese eats the mouse, let's say the probability is 0.2, and the mouse, cheese, eat, and so on, the probability is 0.001, right? You see that when the cheese eats a mouse, it is actually a valid sentence syntactically, right? Semantically it may not be a valid sentence. So the language model should be able to understand the syntax, semantics, and the hope is that the language model will also be able to understand the words knowledge. Now whenever we talk about this probability, what we do, we curate a dictionary, right? Or in other terms, you actually curate something called a vocabulary, right? A vocabulary is a kind of a dictionary, right, where all unique tokens present in a document are available there, right? So how do you create this vocabulary? So let's say you are given a document, you basically move through the document from beginning to the end, right? And you basically collect all those tokens which are unique, okay, and you create this vocabulary. Now what's the difference between a vocabulary and a dictionary? Ideally a dictionary should contain all possible unique words, right? Whereas since the vocabulary is constituted from a document, it may not have all possible unique words, right? So this is the notation. So probability of a sequence of tokens x1 x2 ... xl is essentially we denote it using this kind of joint probability, right? And how do you compute this joint probability? You can use chain rules, right, to break it into conditional probabilities. So p of x1 x2 x3 ... xl is p of x1 times p of x2 given x1 times p of x3 given x1 x2, and so on and so forth, right? So now think about it. What is the meaning of this? Let's say the sentence is the monsoon rains have begun, right? Or have started, right? So what is the meaning of this component, this conditional probability? So it means that let's say given that you have the monsoon rains have, what is the probability that the next word is going to be started? Okay, and how do we do that? We assume that we already have computed a distribution, something like this, okay, where given this context, so this is called the context, right? Given this context, the task is to essentially predict what is going to be the next word, and this distribution is already given to you. Now how do you get the distribution? You got this, you can get the distribution from the corpus itself, right? And then you sample a token from the distribution, right? And let's say this is the sample. So this is the token sampled from the distribution. Let's say sometimes you sampled and you obtained the term arrived. Sometimes when you sample, you obtain the term started, right? When you sample, you get the term, let's say, began, and so on and so forth, right? So, and this is also called autoregressive language model, right? Because you know the context is given, you fetch it from the you fetch the next word from a probability, and you essentially model the entire thing using a neural network, right? In a neural network, simple neural network, let's say a feed-forward network, your input is the context, right? Let's say the monsoon rains arrived, and your output is essentially a word that you want to predict. So essentially you predict a distribution, and from the distribution you sample a token, right? And that's going to be the next word. So now this is language model, right? What is large language model? When it comes to large language model, the word large, we refers to two things. One is the model size, right? The language model maybe is of huge size, right? Large size, and also the corpus or the number of tokens that the model is trained on, right? By the way, there is no threshold of this large, right? There is no threshold of the number of parameters beyond which you can say that it's a large model, and below which you can say that it's a small model. But generally, at least in this time, in the current time, when a model is greater than 7 billion, right, we say that's a large language model. If it is below 7 billion, we call it a small language model, right? Let's say 1 billion, 2 billion models are small language models. Nevertheless, so now if you look at the emergence, we'll talk about emergence. So transformer model, which is the base of all LLMs, right? It was proposed in 2017, but around that time the model called Elmo was proposed, right? And the parameter size was roughly 90 million, right? Or roughly 1 billion. I think roughly 90 million. And then GPT was proposed, which was around 110 million. Then BOT was there, GPT-2 came, right? Robota, Megatron language model, T5. T5 was a billion size model. And then GPT-3 came, 175 billion parameters. And then this Megatron Turing by Microsoft, Gopher, and recently GPT-4. So as you see, over the years, the size of the language model has increased, I think 5,000 times, right, in the last 4 or 5 years. Not only that, if you look at the corpus size, when Elmo was proposed in 2018, right, it was trained on billion size documents, and people started shouting. People said that, look, this is impossible to train, right? And BERT, Elmo models were quite big, and around that time, around 2019, 2020, a lot of researchers came up with ideas like tiny BERT, DistilBERT, small models, right? But then people realized that maybe small models are not that interesting, specifically industry giants. They thought that small models are not that interesting, so we should focus on scaling up and up. And we see these days also people are just scaling up the models. God knows when this will stop, but at least people like us, academicians who are poor in terms of research equipment, GPUs, TPUs, money, etc., we focus mostly on small language models, and we feel that eventually people will realize that small language model is something that people should adopt. Nevertheless, so we do not know the parameter size of models like GPT-4, Gemini, and so on. They are black box models, but at least from the Twitter universe, we came to know that the model size is about around 1.76 trillions, and so on. So this is the landscape of large language model. Okay, this is the, now look at the position of large language model in this ML world. So we have AI, right, which consists of both supervised and unsupervised methods. We also have methods like rule-based methods, planning, right? Then a subset of this is machine learning, where we basically give models a data, and the model automatically figures out the rules. Within that, we have deep learning, where we have deep neural networks, multiple layers, and within deep learning we have this large language models, where now the model is capable of generating things, right? Generating text, generating images. Now large language model is essentially is a generative model for text, right? But again, there are large multimodal models for images, videos, and other multimodal content. Okay, so let's look at the let's look at the evolution of language model, a large language model. Okay, so way back 1960s, 1970s, MIT lab, right? They took a pioneering attempt to design chatbots, right? So ELIZA is the first chatbot which was developed by MIT, and this was a very simple rule-based chatbot which was able to interact with human being. And then, you know, during 1980s, you know, I think the perceptron was introduced in 1960s, and then because of this Minsky's proposition that perceptron is not able to classify Zor problem, right? It was completely stalled. And then I think then in 1980s, around 1980s, 1981, multilayer perceptron was proposed, right? And people also invented the concept of backpropagation, gradient-based update. Around 1995, 1996, LSTM was proposed. It's a version of RNN, right? NVIDIA introduced this GPU, right? Graphics processing unit in around 2000, and then IBM has been one of the pioneers in machine learning, right? So IBM Watson, you know, dominated the entire world of AI around 2000 and 2005-6. We all know the Jeopardy challenge, right? Where IBM Watson has essentially beat the quizmaster, that human quizmaster. And then Facebook introduced their FAIR lab, right? Facebook AI Research Lab around 2007. Google Brain introduced this Google Brain lab, Google Brain project in 2014, 2015, right? Google introduced their unique computing tool called TPU, right? Tensor Processing Unit. But behind the scene, there was another company which was actually emerging, which is OpenAI, right? So in 2017, in 2016, 2017, Stanford came up with this quad data set, which is one of the benchmark data sets, right? Stanford question answering data set. And in 2017, Google Brain, Ashish Vaswani and his colleagues from Google Brain, they proposed the idea of transformer, right, which is the breakthrough. And let's see what happened after that. So post transformer 2017, remember it was proposed by Google, right? This is the paper, attention is all you need. You see people from Google, and I recently came to know that none of these people actually are there with Google these days. They all left. I'm not sure though, but again, in 2018, right, Google again proposed a model called BERT, right, bidirectional transformer language model, and a unique concept of masked language model was introduced, right? This was more of a pre-training concept, right? The transformer was mostly introduced for the task of machine translation, but then in 2018 BERT was introduced and it showed superior performance across multiple tasks. It showed a kind of a state-of-the-art result on 11 tasks, but at that time, as I mentioned, right, people thought that no, BERT is too big, right? We need to design small models. So digital BERT, tiny BERT, mobile BERT, and many small versions of BERT were also introduced around that time. And then someone, as I mentioned, someone was waiting for the right opportunity, and OpenAI, you know, basically also started designing their models. While BERT and BERT-like models are encoder-only models. We'll talk about what is encoder-only models, right? In transformer, there are two components. One is called the encoder layer, other is called the decoder layer. So BERT and the follow-up of BERTs, those models mostly focused on encoder part of it, whereas OpenAI solely started focusing on the decoder part, right? And then in 2018, they wrote the first GPT paper, right? Remember this gentleman, okay? So So this gentleman is essentially responsible for everything. I mean, he is one of the, I mean, I would say he's one of the stalwarts. And he, Ilya was, if you know AlexNet, right? He was the proponent of AlexNet, and he was a student of Hilton and other authors along with Ilya. So they wrote AlexNet, and then then he joined, he co-founded OpenAI, right, along with the other members. And his team wrote this paper, GPT, the first paper, decoder-only model, right? And then right after 2018, in 2019, GPT-2 was introduced, right? Again, this guy, and the beauty about this model GPT-2 was that now, so GPT-1 was a tiny model, because a small model, because there were 117 million parameters. Now in GPT-2 there are 1.5 billion parameters, 13 time increase in terms of number of parameters, also in terms of number of tokens, right, that the model can handle. So GPT-1 can handle 512 tokens, but GPT-2 can handle 1024 tokens. And then we essentially understood or realized the beauty of scaling, okay, with small changes in model architecture, with only scaling, with only parameters and data sets, where people have seen performance improvement across multiple tasks, right? Reading comprehension task, translation task, summarization task, question answering task, right? With only increase in the parameter size. In fact, there are specialized models, for example, pointer generator method, PGNet, for summarization, specifically designed for summarization, right? There are specialized model for reading comprehension, trained specifically for those tasks. But people have seen that these kind of generic models like GPT-2, right, which is trained not for a specific task, right, only a pre-trained model with zero shot kind of setup, with no examples, zero shot setup, the model essentially starts outperforming existing baselines. But you know, Google is Google, so they were also in the race. 2019, Google introduced this T5 paper, right, text to text transformer, Colin Raffel and their and his colleague. And this is the paper where they showed that how you can unify all the tasks to a text to text problem, right? Be it a regression problem, be it a classification problem, a generation problem. So you feed some instruction, and the model will return a text. A text can be a number can be treated as a text, right? And anything that you can think of can be treated as text. So in this T5 model, they basically unified all the tasks as a text to text model, text to text transfer model, right? There is another giant, Meta. Okay, so Google and OpenAI, they had been kind of fighting, but Meta was also in the race. 2019, Meta introduced this famous paper called Robata, right? Some of you know that this paper had been rejected multiple times. I think recently 2022 or 2023 it was accepted. That's what I came to know, but it has been rejected. It had been rejected several times. But this is one of the pioneering papers. Okay, Robata. So in the Robata paper, they understood that the BOT model is essentially undertrained, right? So can we think of beta training BOT models for other tasks? They also proposed this model called XLM, right? This is cross-lingual model, right? Meta, as you understand, Meta has a lot of multilingual data, right? Because of their platform. So they built this XLM model, and a series of follow-ups of XLM has also been proposed, right? But OpenAI was very strict to their policy, right? Scaling up. Okay, GPT-1, GPT-2, 2020 they introduced GPT-3. Again, this guy. Okay, and GPT-3, first time we observed some interesting phenomena called in context learning, right? Prompting in context. Prompting was there in GPT-2 also. So now the parameter size is 175 billion. Okay, But the fun fact is that from now onwards, OpenAI will no longer be open. So they started stopping, basically they stopped disclosing their models, their training protocol, their data sets, and so on and so forth. Google also thought that maybe this is the right option, right strategy, not to open source the model. So Google in 2022 they proposed this model called Palm, right? This is essentially designed for conversational setting, and Palm has a size of 540 billion parameters. Okay, so again, Google stopped open sourcing their tools. In between 2021-2022, we have seen many models, right? Microsoft, in collaboration with NVIDIA, they proposed this Megatron Turing NLG model, right? We have seen DeepMind, Google acquired DeepMind in 2013, I guess, 2013, 2014. So DeepMind introduced Chinchilla AI, right? They also introduced this Gopher, right? Google introduced Lambda, right? And then we have seen models which are specifically designed for codes, right? For example, CodeGen, right? Codex by OpenAI, and then we have also seen other models during that time, but these are the main models. Okay, so then Meta thought, since Google and OpenAI they stopped open sourcing things, let us focus on open sourcing the model, right? Because it seemed to be very difficult to beat OpenAI, frankly speaking, OpenAI models that time. Maybe the other option to essentially grasp to dominate the world is to make it open source, so that at least medium size companies, small size companies, they can use this open source model, and then they can also think of retraining the model, for example, right? So Meta, Facebook, so they propose these OPT models, right? OPT series model from 125 million parameters to 175 billion parameters, everything in open source. And then suddenly in November 2022, ChatGPT was introduced. Okay, and the rest is history. So we knowingly and unknowingly started playing with ChatGPT, right? We kept on giving data sets to OpenAI for free, right? And OpenAI essentially started improving their models from our data set. But nevertheless, in 2023 also, this race continued, right? Google introduced their bot model, right? Meta kept on building their Llama series, right? Llama 1, Llama 2, and so on, all open source models, right? Suddenly, this guy, right, this new company called Anthropic, they came into the picture and they started building their Claude model. Okay. In March 2023, GPT-4 was introduced, right? It's a multimodal model. And then again, as I was mentioning, that at least some corner of this world, there people have been thinking about small models. And this guy from Mistral, from a French company, they thought that let's try to build a small model, right? So they focused on small models like several billion, 1 billion, 2 billion, and Mistral AI was introduced. Mistral had performed quite significantly well with small parameters for reasoning tasks, right? Elon Musk, right? His company XAI, right? So XAI introduced this Grok model, okay? And late 2023 December, Google essentially unified or merged all their bot models, and they started calling it as Gemini. Okay, so but in 2024 we have 6 months, I think we have 6 to 7 months, and we have already seen a lot of new models, right? Gemma 2 was introduced by Google. Then GPT-4o mini version of mini GPT was also introduced recently. Llama 3 was also introduced, and Mistral also started building their code models. Okay. So this is the history. I hope I have been able to cover major parts of LLMs, but of course this is a non-exhaustive list. There are plenty of such models which exist, and people use them quite efficiently. But in I think late 2022, people also realized that these kind of LLMs should not be considered as a all-in-one solution, right? People started building specialized models for, let's say, for stock market prediction. Bloomberg AI, for example, Bloomberg LLM is a specialized model, right? Allen AI, they also introduced their own models, and so on and so forth. But given all these things, why do you think that this course should exist, right? This course should exist because I feel that apart from scaling law, right, there are many small things, many small aspects of LLMs that one should understand, right, to build maybe LLM from scratch, right? And we should know these LLMs because of this emerging the emerging properties, right? One such emerging property is, of course, in context learning that we have seen, where with small examples, right, with a few examples, right, the model should be able to perform well on tasks which the model has not encountered before, right? So zero shot, few shot cases, ideally how in context learning works is not very clear. Specifically cases like chain of thoughts, right, tree of thoughts, and so on. But people have been working on interpretability, and of course LLMs are widely adopted in different industries. Google has adopted. Microsoft has been collaborating with OpenAI, right? Microsoft Bing's data is being fed to GPT-4 for better processing, and so on. And Microsoft Azure is also one example. We should take this course because apart from learning how these models work, we also should learn where the model fails, right? For example, hallucination. We all know that models hallucinate, right? What is the root cause behind this hallucination? How can we quantify hallucination, right? Most of the models are biased towards societal aspects like gender, race, color, and so on and so forth, right? Models are toxic because these models are trained on open source data. Maybe the data sets are not filtered properly, maybe the data sets are not cleaned properly, right? And of course for the purpose of security, right? Let's say if you know the inner principle of large language models, you should be able to know that where the vulnerabilities, right, where an attacker can attack, and how this vulnerability can essentially lead to erroneous results and outputs at the end of the day. Okay, so as I mentioned, there are 5 modules. In the basic module, we'll talk about NLP. We'll not talk about NLP. We'll take one lecture to introduce NLP, and then we'll have a couple of lectures on statistical language models. Then we move to word embeddings and neural LM. We'll look at the architecture, vanilla transformer, and the different types of retraining methods: encoder only, decoder only, advanced attention, and mixture of experts. Learnability aspects, we will see scaling laws, alignments, in context learning, PFT, knowledge distillation, right, instruction fine tuning, and so on. User acceptability, we look at RAG, reasoning, and tool augmented methods, right, and so on and so forth. And then we look at ethics and other aspects of LLM. This is the last slide. If you want to take this course, you should have hands-on experience with Hugging Face, Colab, Kaggle. There are lots of publicly available data sets, right? And last but not the least, this is the rule of thumbs. You see, these days, hundreds of papers are coming every day, right? If somebody is saying that top layers are important, somebody is saying that no, bottom layers are important, somebody is saying no, don't fine tune, do more pre-training, and so on and so forth. Lots of ideas from different gurus, right? Different philosophies. So the rule of thumb is that never believe in any hypothesis until you experience it. If you experience, if you see through experiments that this is actually happening, then you believe it. Otherwise, you should not. Okay. If you have any query regarding this course, you feel free to send me an email. Okay. Thank you.